Well, hi everyone. It's my pleasure to introduce Professor Lenka Zdeborova, who is a distinguished physicist and computer scientist at EPFL, where she leads the statistical physics of computational laboratory. So her main work merges statistical physics with machine learning and optimization, bridging theoretical physics, mathematics, and computer science. And today she will be talking about a phase transition between position and semantic learning in a solvable model of thought product attention. So thank you, Professor Lenka, for joining us, and the floor is yours.
Thank you, Mohammed, and thanks everybody for coming to listen. I will share the slides, that's the right ones. Okay, so as said, I will be talking about phase transitions in a toy model of dot product attention, and you will see the two phases will be between something that I will call semantic and positional learning, and I will explain what I mean by that. This is a joint work with Florent Chakala, who is a long-standing collaborator of mine, and two PhD students in my group, Hugo Cui, who just graduated yesterday and is joining Harvard for postdoc soon, and Freya Behrens, who is a third-year PhD student. So kind of the goal of my current research is to understand what's going on in deep learning, LLMs, AI, all that, with this kind of high-level idea of even if we are not maybe immediately relevant in a single paper, we hope that on a mid-term or long-term, we will understand things enough to make the models more efficient, use less compute, less data for the same performance, understand how to actually do things so that the models are aware of the uncertainty properly and have somehow the right model of the world. And then things like fairness, safeness, robustness, explainability would hopefully follow from that. And so the kind of overall idea is if we understand better, we can make it better eventually. And in order to proceed, we first want to understand the simple things first. Somehow seems reasonable. So I just have 3 slides to kind of about the traditional supervised learning with feed-forward networks, what that is. And then I will use that to kind of compare to what's happening in the attention layer. So just to be on the same line, right? Supervised learning is this task where we feed inputs and outputs to the computer and ask the computer to find a function f, w, parameterized by some weights w, so that the function is say +1 for a cat or -1 for a dog for this like very toy classification task. And only say 20 years ago, we didn't really know how to do that. And now, of course, neural networks do that. And what a neural network is in a sense very simple. It's just a ansatz, a very particular ansatz for what this function w is. And even simpler ansatz would be linear regression. That, I'm a physicist by background, and every physicist did some physics experiments. There we always fit our points with a line or a parabola or something like that. So that's an example of linear regression, where the function would just be parameters times the inputs, scalar product. Or maybe some pointwise function on that. If say we want to output +/-1s, we may want to put here a sign. A neural network is just a recursively applying the same idea L times, where L will then end up the number of layers. So we take the data, multiply it by a vector of weights, apply pointwise and nonlinearity. That's kind of our new features. Then we treat them as if it was a data, again, multiply by a matrix, etc. And this constructs our function. So said like that, it's very simple. This is just a picture that we use to represent that function. And then the way that it is trained is you take many examples that are labeled in this traditional supervised setting, computer, and train with some variant of a gradient descent on a loss that is some kind of similarity between the labels and the outputs of the current network, minimizing over the weights. Okay. So that has been our business for a decade, largely, or maybe not for all of us, but till this came, right? So I was not believing in 2020 that I can go to a window. I just ask, like, if you should say one key progress in AI in the last 5 years, what it would be. And then it answers, large language models based on architectures such as GPT-3 and what these models do. And then you ask, okay, but what are really the main elements behind this GPT? And can you be concise? Otherwise, it gives you this list of 20 items. And it says, okay, it's really the architecture, transformer architecture with the self-attention mechanism. That's, and then the way it is done. It is done. So when I see that, it's like, okay, I want to understand the simple things first. So I need to understand what this self-attention mechanism is actually doing compared to the fully connected layers that I studied for 10 years before that, say. So when then you go to what it is, right? You can say a lot of things about what transformers are, but the key element there is this one self-attention layer. And it's just a layer, as the fully connected layer is a mapping of the signal from some d-dimensional space to some d-dimensional space, or maybe not, doesn't have to be the same dimension, but from some high dimensional space to another high dimensional space. The self-attention layer is also just a mapping from a dimension, from a space to a space, but this time it's useful to think about the dimension of the space to be two-dimensional. There are these two sizes, D and L. So D in the talk will be the dimension of the embedding, and L will be the length of the sentence, right? So okay, so it's not only for vectors, it's for sequences of vectors, but it still maps sequences of vectors to sequences of vectors. And then, okay, people give all kinds of images of what it actually does. Maybe some of you actually understand these images. I never do unless I actually write it in math. So what this mapping is, it's simple. It's just summarized in these two equations. So these tokens that come in, and the J will be standing, J indices will be standing for the positions of the words in these sentences. And then xj or I will be d-dimensional vector. D is the dimensionality of the embedding. So what one head of self-attention layer does, it maps the token through this value matrix that will have size d times some d value, doesn't have to be the same, and then multiplies it by this attention matrix that I will call aij, and ij will be going from 1 to L. And the aij is this dot product self-attention matrix that is in most of the currently used architectures taken of this form, where there is this is just a normalization, right? So this function is usually called softmax, this exponential divided by the exponential summed over this index. But what comes to the exponential is a dot product, that's why it is called a dot product attention, between two vectors. And how we obtain each of the vectors, we take a key matrix or a Q matrix that have sizes something that we can choose, dk, that needs to be equal dq, and the other size must be d, must be matching the dimensionality of the vector. So we multiply this matrix, this vector, this gives us a vector, then we dot product these two vectors, and we have our attention matrix A. Okay, that's how this works. Now, so that's how people then represent the transformer architecture. So again, what I will be looking at is a one component, this orange component, this multi-head attention, not multi even, one head of this attention layer. So I will be kind of theoretically probing what that one component of the transformer architecture is doing. And now in the title, I had this play between the semantics and the position. So let me explain first on a very simple example of a sentence what I mean, and then I will define it more mathematically using the objects that appear in this self-attention layer. So there's a sentence, the cat likes red apples, for instance. So the words in the sentence have meaning, semantics. For instance, if I change apples by balloons, it's not the same sentence, the meaning changed. So this kind of vector of embedding that corresponds to the word, that I will refer to as semantics. And then there is the position of the word. So if I switch cats and apples, I get the apples like red cat. Well, that also doesn't have the same sense anymore. So the sense is also included in the position. Okay, so said like that, okay, it's some triviality. But then how will this actually appear in the math that defines the self-attention layer? So that I summarize here. So that's in other words, still said what the self-attention layer is. There's again still this sequence of tokens, of L of them, of d-dimensional tokens, that is being multiplied by a matrix, the attention matrix A. And what is usually done is that one adds a vector, that is the positional vector, to this matrix, to this sequence of tokens X in this way. So actually the attention doesn't act on the axis directly, as I said before, it acts on the X plus a position. And those may be learned or not learned. In our work, we will actually not learn the position encodings, we will be fixing them. And so these must have the same dimension, and there are still these learnable Q, query, and value matrices. So once we have that and we define, so we see that the attention matrix, maybe back, depends both on the X and on the, this is a matrix, and if you write it now in components, so it depends on the positions, on the I and J. So in general, it depends on the embeddings, xi, xj, and also on the indices I and j. And then when this attention matrix will actually not depend so much on the embeddings themselves, but will depend on the positions I and j. I just switched it here, sorry, it's the other way around. This should be whitened. So when it depends on the y and j, it's the purely positional. And when it depends purely on the embeddings xi and xj, it's purely semantic. Sorry, I should have just switched it. This belongs here and this belongs here. And so what we will want to investigate in our simple model is when does the attention that is learned implement rather a positional learning, or when it implements rather a semantic learning. And again, later on, I will be like one step more precise about what exactly I mean by that. But so let's go. So one thing that, the last kind of term in my title that I did not explain yet is the phase transition. And well, you have some notion about what the phase transition is from your high school physics, but where we kind of get thinking back about phase transitions is when we see these works on emergent abilities of large language models. Like it looks like some ability of, I don't know, answering questions in certain language or modular arithmetics, or many examples that appeared in these papers and other ones. It looks like they appear very suddenly, at least in some way of plotting the accuracy and the model scale on the x-axis. So it makes one think, okay, is this a phase transition? Is it not? Some people just call it this way, not really, being very precise about how or related or not it is to what we mean the phase transition in physics. So this is this is kind of the third aspect that we want to understand. So before now going on with the paper that I want to present, I have a couple of slides, maybe more than a couple, maybe 10 or so, about phase transitions in learning with neural networks, but somehow before the large language models and the foundational models era. So more in the models of the feed-forward neural networks. Because this is actually something that didn't come up with this paper of emergent behavior. This is something that was around for a very long time. And kind of in general, so phase transitions in general in science are kind of how that kind of comes about in other things than purely physics is kind of nicely and famously summarized in this essay by Phil Anderson that is called More is Different, where the kind of overall idea is that the behavior of large and complex aggregates of elementary particles, but these don't have to be particles, these can be any interacting things, bits or nodes of a network, etc., turns out is not to be understood in terms of simple extrapolation of the properties of the single particle or of a few particles, and instead at each level of complexity entirely new properties appear. So this is kind of how in science, how in physics, we kind of think of this emergence, and it's exemplified by, okay, now I move this window and I don't know why my slides don't want to be moving. Okay, now, sorry. So in physics, this new properties that appear without actually changing anything about how the individual components of the system behave or interact is exemplified with this kind of phase transition as you know it when water freezes or water boils. This is a phase diagram that you may have seen in high school when you put the pressure and the temperature on the axis. Then you know that you have in certain region you have ice, in other you have the gas, the vapor, and in other you have liquid, and you can walk through the liquid to the gas continuously around this critical point. And I like this image pretty much because there is this atmosphere on Mars and atmosphere on Venus, so this kind of puts in perspective the scale of these axes. Okay, so that's physics. But do phase transitions like that? So the key thing here is that a phase transition may appear if there are many elements interacting together, and it purely appears from the limit that you take that there are infinitely many of them, and some quantity that you're interested in, say here is the density of the material, may change discontinuously at certain value of pressure or temperature that would be depicted here. So that's in physics. What about seeing things like that in machine learning? So that's where I was going, that this is not something that appeared in the past few years. This actually perhaps the first paper that very precisely identifies a first order transition to perfect generalization in the sense of test error. In a neural network with binary synapses actually comes from the 90s, so the very early 90s, where they show this test error as a function of the number of samples over the dimension of the samples, and it has a behavior that it goes down in some pretty much linearly looking way and then suddenly drops to zero. Suddenly you acquire that ability to learn that particular target function to zero test error. And then there is another interesting point. I will come back to that in a little more detail. But here the point is just to say that this idea of phase transitions in learning is there for a very long time and has been analyzed in physics. So now I want to show you a little bit how we go about modeling something like that and describing it with mathematics and describing it precisely in a solvable way in a closed form. Like, what do I mean by all that? So in order to do that, I need to kind of simplify the way I'm thinking of this generic task of learning something with a feed-forward neural network, because already showing that there is phase transition on, say, learning CIFAR, well, it's not something that can be readily done. The most key reason for that probably is that the data set CIFAR has one size. So there is no way I can take the dimensionality of that data set of infinity. The number of pixels is fixed. So there is no way I can really carry this way of thinking that as something goes to infinity, some quantity will truly become discontinuous. I may get a numerical picture that looks close to discontinuous, but I will never be able to decide whether it really is or not, because I cannot take this high dimensional or thermodynamic limit. So I need to come up with a model, with a way of thinking of in a sense, abstracting the situation where I can take this limit. And the way this was done in this literature in the 90s is the idea of this teacher-student model of learning a function with a feed-forward neural network. So that's a setting where we don't look at some concrete task of classifying, say, cats and dogs, but we assume that the target function itself has the form of a neural network, and that will be the teacher neural network. So there is some input data, X, d-dimensional, and samples of them. This is my notation. And then we assume that there is some ground truth or teacher or target, however you want to call it, neural network that has weights that can be chosen at random that produces the labels. And then the student network, it sees the inputs, it sees the outputs. It may see the architecture of the network that can only help, cannot make the situation worse, but crucially, it does not see the values of these weights. It has to learn weights in the usual way by gradient descent on the training loss in order with the goal of learning the same function. And then the question is, how many samples do I need in order to be able to learn the same function as the teacher was representing by the student neural network? So this is already, you see, I already put a lot of the complication of the real situation away and assumed that I know what the target function is. I just don't know what were the values of the ground truth weights. So that's what the student network still needs to learn, or some other values that still represent the same function. And in that line of work in the 90s, actually the first one that introduced this teacher-student kind of abstraction or way of thinking about it, they called it the teacher-student perceptron. It was by Elizabeth Gardner and Bernard Derrida. They did two other kind of crucial assumptions. One is that also the input vectors are actually random. So they're just IID from each other, and all the components are also IID. So no structured images, nothing interesting to learn just by looking at the inputs. These are just random Gaussian matrix. And that the neural network, the simplest case to start with, is the one that doesn't have any hidden units. So that's what they started with. I mean, it makes sense as a starting point. And then the interesting thing is that they looked at this high dimension limit where they took the dimensionality of the input D very large, the number of samples also very large, but in such a way that the ratio is fixed, say half or 3 or 10. And this today in statistics, we call this the high dimensional regime, the high dimensional statistics, and a lot of theory in statistics and inference is done interestingly in that regime, because as on one hand, when dimensionality is large, your algorithms may become exponentially costly in the worst case. So there's the bad thing that the dimensionality brings, right? And then on the other hand, when there is randomness in the system, and thanks to the randomness, there is a limit in which things start to concentrate, you have this blessing of dimensionality, where actually things that look very probabilistic, very random, concentrate on deterministic quantities, and that actually allows you to describe in a deterministic way what will be happening in the system in this limit. And this is something natural to the statistical physics way of thinking about it, but to the kind of computational and statistics way of thinking about it, this way of considering the dimensionality comparable to the number of samples rather than fixed and the number of samples much larger, that came much later, maybe in the early 2000s or in the 90s, there were some of the first papers. But this considering this limit was kind of ahead of the time, and that's in a sense what allows the crisp analysis of the learning curves and of the phase transitions. So this is a setting where you can, for instance, compute something that we call the base optimal generalization. So whatever algorithm you will use, whether it's exponentially costly or efficient, polynomial or even like linear in the size of the system, you will not be able to beat the performance of the following estimator, that is writing the posterior probability distribution corresponding on the weights that you don't know, given what you observed, the inputs and the labels. Just using the Bezoar formula, this has this form. And if you are able to compute expectations with respect to those posteriors, then you are able for a new sample to estimate a new label, and no method can beat the accuracy of that particular estimator in the setting that I'm talking about. So that's our baseline. We will want to analyze what this optimal error actually is. And that's what has been done back in those papers by Georgi and Gardner and Derrida, using non-rigorous methods of statistical physics called the replica method. And we kind of got working back on these things about 10-ish years ago, and managed actually to prove that line of work, that all that is kind of rigorously and mathematically well established. So this is what we done in the paper cited here, in this teacher-student setting for a single layer to start with. Then we continued on more complicated cases. This is just to introduce the methodology a little bit. So the form the theorem has is the following. In this high dimensional limit, there is a formula that we call free entropy that has this. On the next slide, you will have the specific expression that is depending on single scalar parameter. So m is just a real number. And that implies both the optimal error that you can achieve, the optimal test error, and a test error achieved by a specific algorithm that we call approximate message passing. And that particular algorithm will be tightly linked to the optimal error. Well, first of all, its performance is given by the same formula. So let me just show you how this formula looks like. What it actually is the limit in this high dimension that I'm considering of this. So the z was the normalization of the posterior probability distribution, and it's the limit of its logarithm over, the expectation here is taken over the data, because we assume the data to be randomly generated. So that's where we get rid of this randomness. We don't need to do it because the theorem actually says if we didn't take this expectation, it would still with high probability be the value that is given by a formula that, if you have never seen it or haven't done the calculation, will look completely non-transparent. But the bottom line is that it only depends on what activation function the teacher used and what this probability distribution the teacher was using to generate the weights. And then is just few integrals over Gaussian variables, or perhaps over random variables taken from the same distribution from which the teacher was picking the weights. And it's an explicit formula depending on one variable, so you can plot it and see where it has a maximizers. And also, as a corollary of this theorem, you get the optimal test error. That is another expression of this type, depending on the maximizer. M star will be the maximizer of this phi m. So that's on the side of what is achievable, irrespective of whether we have an efficient algorithm for it or not. But I also mentioned this approximate message passing algorithm. So here, this is just to give a pseudocode of that algorithm. The way you can think about it is like an alternative for gradient descent for training the network that is very specific, that really relies on the assumptions of the teacher-student model that I'm making, that is that the input data are Gaussian and that the teacher generated random weights. So this is not like a general proposed algorithm that you can use and train your whatever large language model, not at all. It's in a sense a analysis tool, because its behavior is very interesting, because we can show about this algorithm that the accuracy it obtains at every step, it's again an iterative algorithm similarly to gradient descent. So at every step, every epoch, it has a given accuracy. And the accuracy can be tracked explicitly using the same formula that you have seen 3 slides ago. So that's how this particular algorithm is like complementary analysis tool to actually understand what's going on in these systems. Okay, now I stop with the technicalities. You can forget about them. They will come back maybe a little bit but the equations will be even more bulky and hence even more smaller. So you will see. So just now, how this actually leads to the phase transition that I showed you was already obtained in the literature in the 90s. So when we put these methods together, we can plot this picture, where is the test error on the x-axis and the number of samples on the y-axis, and the number of samples per dimension on the x-axis. And this is for the case where the teacher was using sign activation function and generating the waves that were just plus minus 1. And then the student is trying to learn the same function. And the red line is the information theoretically optimal way the student can manage with this sharp drop. So this is already in the limit where everything is infinity. If you were actually simulating it, and in black is this actual simulation of the approximate message passing algorithm that has a sharp drop a little bit later at this point. And okay, I didn't put enough points here, but it wouldn't, you know, for a given size, it would not be like super sharp. It would be going a bit smoother. And as the size is getting bigger and bigger, it would be sharper and sharper. And then in the limit is infinitely sharp. So this is a example of this phase transition, where you see you have kind of two different things happening, one for the information theoretic performance and one for the performance of the algorithm. And in between, you have this phase where this particular algorithm doesn't manage. There's actually a really interesting conjecture that no other polynomial algorithm in this case would manage. And this is a phase transition really in the same sense as we would think about it in the water. We could make the analogy that if say ice, so freezing would be the goal here, freezing would be corresponding to perfect test error, so 0 test error. And being a liquid would correspond to some mediocre test error. Then the phase transition between liquid and ice, so what happens at 0 degrees Celsius at normal atmospheric pressure, would be actually corresponding to the phase transition where, irrespectively of the existence of efficient algorithm, you get a good performance. And then what would correspond to the performance of the algorithm would actually in physics be the temperature to which you can supercool liquid without it freezing. So at this point, this analogy is a little bit imprecise, in the sense that water lives in 3-dimensional space, and thanks to that, there is this physical concept called nucleation, that in this high dimensional or infinite dimensional space at which we are looking when we train neural networks actually doesn't exist. The nucleation doesn't exist. So if we can supercool something, it will stay supercooled forever or for exponential time, which for the sizes we are looking at is equivalent to forever. And this is what creates these lags of the algorithmic performance after the information theoretic performance. So, okay, so this hopefully kind of gives you some idea on how in an extremely simple model of a feed-forward neural network with no hidden units, you can already have this non-trivial concept of sharp drop and a phase transition appearing in the test error as a function of seeing more and more samples over the dimension. So here it should be n over d. I copied from some other notation. Or miscopied. Okay, so here it's maybe a good point if you have some questions about this part, because here is where I will take this way of analyzing things back to the world of the attention layer, and explain this paper that we did at the beginning of this year, where we describe a phase transition, a true one, between the positional and semantic learning. So if you have questions on things before, it's a good point for clarifications or. No, if no, then I can go on.
Question, but maybe I can ask one.
Yeah.
Like regarding the assumption that both dimension number of samples go to infinity. Is there like some extensions of this result when you have the number of parameters also grow into infinity? Like you have three dimensions involved, because we have this over-parameterization regime where of neural networks we see that it's performing.
Yes. So here I showed you the kind of simplest case. You can absolutely have similar things happening so I have, okay, that I could have maybe put that part. So we do have examples, because with this line of work, then before we kind of jumped, oh, let's study the attention layer, we went to studying learning with random features, learning with kernels, learning with two-layer neural networks. And there we looked a lot at the dependence. So so immediately one has three parameters, right? The width is the kind of third parameter. What happens with the width? So there is one case where things are interesting in terms of the width growing, but that's not in the base optimal performance of something, but because of the use of the gradient descent, that actually works worse than, say, this approximate message passing would work. One lags behind, and in such a way that over-parameterizing actually makes the gradient descent work or generalize well in a specific setting, in a setting of a phase retrieval, which is just another variant of this teacher-student model. So there we can see something like that.
Okay.
It's a very simple model of, still learning a pretty simple target function, but now learning it with the over-parameterized neural network and training this network in the canonical way with the gradient descent, and the gradient descent not being optimal. And because of the properties of the gradient descent, seeing this kind of emergence of the zero test error with the width of the network. So that kind of, it can point you to the work where, in this sense, it's also established on a special case, not in like super large generality.
Nice. Thank you.
Other questions? Well, let's go on then with the dot product attention. So that's where, now that I kind of set up the notions, I want to go back to this paper that is the main kind of focus of the talk. So now we have in mind this teacher-student model. So the first thing, so that's the same spirit here. First thing, I need to define the teacher. So it's again a setting where the inputs will be IID Gaussians, but now I also have this sequence of inputs. So each member of the sequence will be an independent IID Gaussian. So the inputs here will be still very unstructured. The only thing that changes is now they are not just d-dimensional, but they are L times d-dimensional. Okay. Now the structure will be in the function. We will again be looking at supervised learning, and we will take the labels to be results of in the same spirit as before, as we took the target function to have a form of the feed-forward neural network. And then that was kind of a setting that at one hand was, a reasonable setting to start at the other hand, and more importantly, if we want to analyze something, enabled the analysis. So here we will have, in a similar spirit, a target function that will involve the attention, and that will also involve a matrix that will be a L times L, if you want, a ground truth attention matrix, but in such a way that it does not, this S will not depend on the embedding X. Whereas this part does depend on the embedding X in the usual way, as the dot product attention does. There is the softmax, there is the embeddings X. The simplification that I'm doing here is, there are two things. I am tying the key and query. So the key and query matrices will be the same. So I'm tying those together. And I am not taking them off. So this matrix W star in general is some dimension times D. And this dimension that I can choose, because then I make the dot product, here I will choose it 1. So this W star is just a vector, actually. and not a matrix itself. So this will be the simplification that will make things kind of analyzable in the large dimension limit. And then I have here this parameter omega that is real number. And for instance, if omega is 0, then this term is not here and only this term is here. So I will call it that the attention in the target function is purely semantic. It only depends on the embeddings and not directly on the positions. Whereas if omega is 1, then this term is not here and it is here. And then the attention, the target attention is purely position. I will just pick some values to this matrix and it does not depend on the embedding. It purely depends on the indices, where in the sentence I am. And then I generate a training set, or the teacher generates a training set from these random axes and using this function as the target function. So that's the kind of how the data was the data model. So it's not some real data, some language or something like that. It's a synthetic data model that is defined here. So now that I yeah, there's a question.
Could you please comment on the normalization by D in the softmax?
Yeah, that's just to keep the things inside of order 1. So usually, so before, okay, I don't remember how I defined it before, but it's similar. So, okay, here I didn't have this 1/d here because I used the sine function. But if I was using, say, a linear function, I better have the variance of these x's to be 1/d so that this product between the vector of plus minus ones and this random Gaussian numbers, so that the product is of order 1. Okay, and that's the same 1/d here, because here I am taking the elements of the inputs actually with variance 1. So sometimes we just put the variance 1/d here and then there would not be 1/d here. So that's just to keep things, d will go to infinity as we anticipate. So to keep things scaling non-trivially, so that the softmax actually does something, so that the argument that goes to it is, strictly between 0 and some large number.
I guess W star is of norm 1 here.
Sorry?
W star is like supposed to be of norm 1, constant norm.
No, sorry. W star is not of constant norm. The elements of W star are of order 1, just like here, right? The elements of W star are 1. So the norm of W is D.
Yeah, okay.
So that's maybe, I mean, yeah, in say random matrix theory, you usually take the norm of W1 and then again, the D would not be there.
Yeah, I see, okay.
So you can either put it in the W or in the X or explicitly here. That's kind of a 3 equivalent way of thinking about it. But it's in a sense the random matrix scaling of things in which you get the Marchenko-Pastur law, so that it's non-trivial, that you're not either like spike trivially infinitely away or inside the bound. And we are looking in that scaling. Because otherwise, things would be either trivially possible or trivially impossible. So we kind of look in the intermediate scale.
But we have another question by Maxime.
Would you read it, or should I? How do I?
Asking which architecture is used by student. The architecture in the beginning of the presentation used.
Well, that's the next slide. Right? We got question on this slide, so I did. So let me go to the next slide, and if there is still unclarity, you ask again, please. Maxim, it was right. Okay, so the next slide, right? So now that we fixed the teacher, what is the student? So is this simplified dot product attention, where to mimic what the teacher is doing, I'm tying the key and query. I am taking it just a vector, not a matrix. And I'm adding the position to the embeddings. And here, the pictures that I will be having will be later for just very tiny sentences of length 2. And then the position can just have 2 values. So I pick some vector, d-dimensional vector mu, and the position I put mu or minus mu, depending whether I'm in the first or the second position. Okay, so this will be the dot product attention layer, and there is only one head and there is only one layer. So then the risk on which I'm training is this regularized square risk, where I am taking f star, which was the target, and comparing it to the output of this very small architecture. And the limit that I'm considering is, as before, the number of samples is large, the dimensionality is large, proportionally so. Again, the proportionality factor is alpha. And then the other parameters, like the length of the sentence, L is of order 1. And the position embedding is chosen. Okay, this actually needs to be the same norm as the X roughly, so this might be actually of order D. This may be a misprint. It's chosen so that the norm of the P and the X is comparable. And then what I'm interested in is the test error, which will then be the expectation on a test set of these two functions, of the difference between these two labels. Okay. So now I can kind of, so how do we solve when we say, it's a solvable model of dot product attention? We kind of bring it back in a sense to the previous situation, like not completely, but technically it's in a sense, the reasons for which technically we can tackle this limit are similar as the ones that were there for the perceptron problem that was modeling the single layer feed-forward network. And concretely, we again have the approximate message passing algorithm that I really like showing here. Really, here the purpose is not to try to understand what all the letters are. I didn't even write it down, but there is an analogous algorithm that is an iterative algorithm of this approximate message passing that again is in principle, you could use it to train, but it's really not kind of a practical purpose for that. It's more an analysis tool. Because at one hand, we can show that the fixed points of this algorithm are actually 0 gradient points of the actual gradient descent that is minimizing the empirical landscape. So that's one side of one part of the theory. And the other part of the theory is we can write the state evolution, this tracking of what this algorithm actually does, and write an analog of this free entropy function that previously I called phi rs phi, that now, before there was only 2 parameters, now I have 1, 2, 3, 8 parameters or equations for 8 parameters that I need to solve some self-consistently. Again, purposefully, I'm making them so small that you don't need to read the details. Just kind of get the spirit that I had this high dimensional problem. Dimensionality was large, number of samples was large, both were going to infinity together. But now I reduced the problem of what the gradient descent is actually doing and where possibly it can be stopping, the problem of what are the fixed points, to a set of equations that are just, so there are actually 8 of them and they have still this index L. But L goes from 1 to capital L, which in our case, our example is 2. So I just have 16 equations that I need to solve self-consistently. And there is a meaning of all these parameters. In particular, 2 of them on the next slide will be interesting. And then once I have the fixed point of these equations, I can express both the test error and the train error of the little architecture already in that thermodynamic limit, in that high dimension limit. So again, the details of the equations are daunting and one would have to go to much more detail, but the spirit of them is very much the same as the line of work that I presented previously, that is kind of around for a couple of decades and started in statistical physics. Now we know how to establish these rigorously using corresponding proof techniques. That's kind of how the technical part of the paper goes. So now, as I promised, 2 of those parameters, actually here, the M and the theta, will be particularly interesting. And we call, so all these parameters, we call them order parameters, But now this M will be what we will call the positional order parameter, because what it actually is, if you trace in the algorithm what it is, was the meaning of this parameter, it's actually just the correlation between what the algorithm is learned at the minimizer and this vector that I put in to take care of the positional embedding. So it is directly the correlation between what is being learned and the positional embedding. And then there is this other parameter theta that we will call the semantic order parameter, because that's a correlation between what is learned and the ground truth value of the key and query of the target function. So this is telling us kind of how much the semantics matters for what is learned. And then what is drawn here for some particular choice of my parameters, so I choose this parameters omega and s and variance of the Gaussians in my data, and how the teacher chose this key and query vector. So that specifies the target function. And for the specific target function, I plot the values of these order parameters as a function of, again, the alpha is the number of samples over the dimension. And I see that before a certain value alpha c between 1 and 1.5, the global minimizer of the loss function is reached where the theta parameter, so the semantic order parameter, is essentially 0, whereas the positional order parameter is positive. And above that value, there is a different minimizer of the landscape that starts dominating. And that one is the other way around, that the positional order parameter is 0 and the semantic order parameter is positive. So what this is telling us that once we reached a number of samples that is, 1.2 times the dimension, we start to be using the semantics for the learning. And below that, we were using the position only. And if we translate now the same values, as I said, we have not only the values of the parameters, but as a direct consequence, we have the value of the test error. And here always the lines, that's true also here. The lines are the asymptotic theory, and the points are actually the runs of the gradient descent to confirm that this is indeed what the gradient descent is finding. And this picture is for the test error. And we see that in the region where the positional learning happens, here, the test error is somewhat larger than in the region where the semantic learning happens. And that at this threshold alpha c, there is a sharp drop from one to the other. So there you go. That's in the same sense as I was showing it to you for the learning with the simple perceptron, which really is again the same sense as the models we are using in physics to describe something like a phase transition in water or in magnets, or in magnets, there would not be drops, there would be continuous changes of the behavior, second order phase transition. Here it's a first order phase transition, but the kind of theory that we do behind to describe this is really the same one as we use in physics to describe these concepts. For the price of making this a very, very simple setting with just one layer, one head, tight key and query, value is not there or not learned or identity, right? So we simplified a lot, but we are getting kind of very crisply the right concept here. And here, this is a phase diagram when I change the omega parameter. So remember, the omega parameter was in the target function when it was 1, it was actually purely positional target. And when it was 0, it was, so that would be high up is purely positional. And when it was 0, it was purely semantic. And the phase transition actually shifts with this parameter omega. So if the target, if the omega is larger, that means that the target is more semantic, then I need more samples. No, sorry, when the target is more positional, then I need more samples to actually bring in the phase transition and start learning from the semantics. So that kind of goes in the direction in which we might expect, but it's kind of nice to see that indeed there is something like that. There is a sharp change of behavior from one region to another. And with this, I'm kind of going to the conclusion. So this is just a start of our, investigation of what actually happens in these attention layers, where we kind of achieve two things. We bring the concept of the attention mechanism to a setting that is actually solvable in the thermodynamic, in this high dimension limit with very precise tools. And we locate this kind of interesting interplay between this positional and semantic learning. But there are many other things and questions that we are asking and should be asking and hopefully answering. For instance, is the softmax that we were using crucial? Would the same happen if there was just a linear attention or other nonlinear types of attention? What about the skip connections that are super crucial to stabilize the training? Would they actually change the story? What if we added a learnable readout or had multiple heads or multiple layers? What if now we were looking at explicitly at the dynamics of the gradient descent and not only at its fixed points? What if we now added structure in the inputs and do not consider them anymore Gaussian and IID? And what if we started asking questions like, what is there beyond the dot product self-attention and how we can do certain tasks even better? So all that, in principle, this model opens a stage to investigate these questions mathematically, analytically, compared to numerics to kind of see whether we are doing the right thing. That is there to be done. And kind of more broadly, here I just have one slide that more broadly shows some directions about things at which we are looking in the group, such as looking at the structure of the data, right? Clearly here that I'm assuming that everything is Gaussian, IID, unstructured is very, very simplified. And we can say nowadays a lot beyond that about equivalence to Gaussians or hierarchical data or kind of what to do beyond that, about benefits of depth, why actually do we need more layers and how to kind of crisply pin reasons for that, analyzing explicitly the gradient descents, quantifying the uncertainty that I was mentioning at the very beginning, or looking at other conceptual things in learning, such as learning with diffusion-based or score-based models and how that brings the generative ability of these neural networks. And I will stop here with just some fun picture of the group. Again, with Florent, with whom we work very closely, and this is a lot of the current and couple of the past members that we all met this summer in a conference. And I will open for questions if there are still some.
Nice. Thank you, Lenka. That was very interesting talk. We have like few questions by Maxime. One of the questions he's asking, is it known how transition point behaves in the positional limit? Omega goes to 1. When you take omega goes to 1, is there?
Yeah, I think it just goes to infinity. Just looking at the figure.
Okay.
Yeah, there was nothing. It's just going to infinity. I would have to confirm that, but yeah, we didn't. We did ask that, but okay. To be sure, I would have to confirm that, but I think it just goes to infinity.
He's asking at which speed? Is it like some power law kind of?
Oh, okay. No, we didn't look at that. Yeah, that's something that in principle can be extracted from the equations, but we didn't look at that particular speed. that would be interesting to do.
I may have one question about
And
the
there is also, so P was not learnable in the student, right? So in our case, the position is fixed and the positional encoding is fixed and not learnable. Yes.
So related to this question is like, so in the experiments or like the simulations that you did, like what is the correlation between mu and W star? They are both orthogonal?
Nothing. Yeah, they're orthogonal.
So
we
maybe
take mu1, I think, in the simulations. I could have, so it's just identity vector, whereas W star, it's a random IIT vector.
And have you tried like on the same sitting making like W, even like through simulations making W star and the mu trainable, like this positional embedding, to see if there's some.
So W star is trainable,
Yep.
right? But you're saying making mu trainable.
Yeah.
Um,
Through simulations to see how close it's. Because after
so we didn't. My impression is that nothing much would change. But okay, that's again something. Yeah, we didn't look at that. That's
because beyond the phase transition, like alpha C, you have let's say good correlation with W star, but yeah, it's completely so it doesn't basically rely on the position at all to make decisions. Whereas in current
yes, it
implementation,
doesn't.
in current implementations, we know that like if you switch the positions and you make like
Yes, that's some particular property of our model. That's we were kind of a little surprised that we actually had these fixed points where the order parameters respectively are exactly 0 in the two phases. One would somehow, or at least I expected that we will just get maybe one bigger in one phase and one bigger in the other phase. But here it was really this dichotomy with one of them really not contributing anything. So that must be some particularity of the model. And it would be good to kind of like there are many directions in which this can be generalized. And definitely tracing what controls this, that this order parameter is exactly 0, is one of the questions that that would be interesting to look at.
we have two more questions. If you
Okay.
maybe stop there.
What are the connections between diffusion models, score-based models, and phase transitions? Oh, so yeah, we have this recent paper on the diffusion models and score-based models in a setting where, in a sense, the learning from data is put aside. You're looking at much simpler setting than when you actually need to learn the distribution from samples, where you, in settings where you actually have explicit access to the, to the Boltzmann measure, but these usually come in a way that you don't have the normalization. So even though you have explicit expression for the distribution from which you want to sample, and you don't need to learn that from data, you cannot learn more from data. It's something where the normalization is some high dimensional integral, so you don't have access to that. So these distributions are difficult to sample in general. And for a lot of these distributions corresponding to what we call spin glass models, so models of magnets and disordered magnets and glasses, we actually have a pretty good understanding for the traditional samplers, such as Langevin dynamics or Monte Carlo Gibbs sampling, about the regions of parameters in which they work in polynomial time and in which they don't work in polynomial time. And again, the boundaries between those regions correspond to phase transitions. And what we did in this recent work on diffusion and score-based models, we actually back-to-back compared the performance of flow-based sampling to the Monte Carlo. And we found interesting things. So sometimes they exactly go back-to-back. When one is possible, the other is possible. When one is not possible, the other is not possible. So that's somewhat less interesting. But we also found cases both where Monte Carlo does not work and diffusion-based sampling works. So that's maybe a region where you would hope for based on what we see kind of in the area of machine learning. But most surprisingly, we found a region where Monte Carlo works and diffusion-based models do not work. And the reason for which they do not work is that in the flow, as they are denoising as they're removing the noise from the just purely Gaussian noise, they actually encounter a phase transition. And that makes them fail. That kind of breaks the direction of the flow and they're not sampling anymore. So again, we are not saying that these are super generic, right? These are constructed models. This may happen in practice or not. Like we don't in particular have any evidence that it happens in practice, but at least conceptually, it is interesting that you can have a crisply defined model where sampling with traditional Monte Carlo is easy, but sampling with flow-based or diffusion-based or in this kind of stochastic interpolance language by Eric van den Eyden and Michael Albergo that I like very much. It's all the same. Those do not work because they encounter a phase transition in the flow path. So I can point you in the paper if you're interested. It just appeared in PNAS like yesterday or 2 days ago, but unrelated to the kind of attention work that I talked about today. Okay, the second question. The experiment suppose that we know the probability distribution of the input data. However, in real data sets, probability distribution is untractable. Does your finding about phase transitions apply to real-world data sets where we cannot generate training data using teacher model? So if it did, I would have told you, right? I mean, we don't know in the real world data sets how to actually say whether this emergence that we are seeing is a phase transition or not, right? So different people may have different opinions, but this question is not settled, right? That's objectively the case. And that's the goal here. So right, how kind of this theoretical investigation of these models proceeds. So it starts at some setting that arguably threw away a lot of the interesting things, but hopefully kept the key ingredients that kind of still make it make sense to, we are still talking about attention, there is still some learning problem, there is still some input data, output data, right? And once we have that, then we start putting things back in. So I actually went through it quickly, but I like to think here of this diagram that the data are structured, the architecture is complicated, and the algorithm is kind of the algorithm that we end up using. And these three things interplay in interconnected way. And we, in a sense, in our modeling, start with trivial data structure. I completely admit to that. Trivial architecture, right? It's just one head, one layer. The algorithm is not even, right? We start with this approximate message passing, not even gradient descent, but then we start adding things back. So here, the structure in the data, right? We go away from the Gaussians. And for instance, in the case of the kernels or random features or single layer neural networks, we actually see that there is this Gaussian equivalence that whether we train those networks on MNIST or on a Gaussian data of the same covariance is the same. So those particular models only pay attention to the covariance in the data, which of course will not be the case for more complicated data or more complicated models, but kind of starting to understand what in the data actually influences the performance of the model, right? I just can't go directly to the real situation. I just go step by step from the simple situation. The same about the architecture, the same about the particular variants of the algorithm. So we know now quite a lot about how to analyze the gradient descent multipass. But if you start kind of adding all the tricks of the trade in, then I will not know yet. So hopefully we will get there. Not maybe on the startup time scale, but on the academic time scale we will.
Sure. And there is maybe one final question by Neil. He's asking about if there is a similar analysis when using multiplicative positional information, like rotational position embedding.
Okay, that's a good question. We didn't think about that. So no, so I should say no, right? There is no symbol analysis, but that doesn't mean there couldn't be one. That's something that we could think about if it was of interest.
Okay. I guess we can maybe stop here. Thank you very much, Professor Lenka, for accepting our invitation and for the very interesting talk.
Okay, thank you for all the questions and for inviting me, and have a nice day.
You too. Thank you very much.